Thank you. So here's my title, Transition States in the Excited State. So I just will remind people what we mean by reaction dynamics in the ground states. So this is our potential energy surface, there's reactants, there's products, and there's some forces, some potential energy surface, which governs the outcome of these reactive encounters. And this yellow path, the minimum energy path between reactants and products, we call the reaction coordinate. And somewhere, typically along the reaction coordinate, we have a barrier, the maximum of which we might call the transition state. Now, my PhD supervisor was John Polanyi, and he spent a long time thinking about these types of collisions, A colliding with BC. He shared the Nobel Prize for this work in 1986, and some of you in the audience have worked longer in this field than I have. So I just would give a quick reminder of some of the things that John Polanyi had made contributions to. And these are known colloquially as the Polanyi rules. And what it does, it relates the topography, the shape of the potential energy surface, to the propensity for reaction and the outcomes of reaction. And John called these early and late barriers. So here is a symmetric transition state where the transition state is exactly in the middle. But you can also, for different systems, you can have an early barrier or a late barrier. And it turns out that whether it's translational or vibrational energy which gets you over the barrier and reacts, or is an outcome of the reaction, depends really on the location. And these became known as the Polanyi rules. So I often wondered whether one could develop Polanyi rules for polyatomic molecules, for excited state dynamics. Are there simple rules that we can try to extract and apply to polyatomic reaction dynamics? And it's not so obvious that this is possible. Why does a dynamical perspective matter? So I will argue to you that this is what you're doing right now, at least I hope, if you're not asleep yet, which is that you're looking at my screen. And if you're looking at the screen, then in your eye, there is a molecule called rhodopsin, which is a transmembrane protein, which sits in your eye. And the first step in vision was measured by Schenck and Matthews a long time ago. And it's measured to be something like the 10 to the minus 13 second time scale. We know, however, that from the point of view of function, vision, that the overall visual response is 10 to the minus 1, or maybe, let's say, at best, 10 to the minus 2 seconds. So I could certainly argue, from the point of view of a functional relationship, that the fact that the first step in vision happens to be in this time scale is completely irrelevant to its biological function. Because as we know, 30 frames per second looks continuous to our eye. So does the first step in vision really need to be so fast? Is it just a curiosity, or is there a reason for this? And the answer is yes, it has to be so. And the reason why is because there are fast competing dissipative processes which will basically remove the energy from this transmembrane protein and dissipate it to the surrounding protein, the aqueous environment. And because these dissipative processes really are there, nature had only one choice, which it had to be faster than the sum of all competing processes. So if I may say it in my words, nature designed this device for speed. It had to be fast or it never would have worked. So in other words, dynamics is really central to the function. And this is my only real take-home message, which is that I would say a grand challenge in the chemical sciences is to bring dynamics in on a more equal footing with structure-function relations. We have 100, 150 years of structure-function relations, but for active processes, for dynamical processes, we need to bring in dynamics on a much more equal footing. And I think that's a challenge, and I think I'm going to argue to it's an important one. So I'm going to be talking about excited state reaction dynamics, where obviously there are fast processes, where both charge and energy are flowing within the excited molecule, and they do so in fast timescales. There's a picture from Joseph Mikkel and Vlast's book. And there's something here called a conical intersection, which I will go on to say a little bit more. There are some experts in the audience. I will give it just a very rudimentary introduction. So here's my question. Will there be Polanyi rules for excited state reaction dynamics? The first question is, what is the transition state? What plays the equivalent role of a transition state in excited state reaction dynamics? And I think the answer is pretty clear. It's this conical intersection, which is really an electronic degeneracy in polyatomics. It's a 3n minus 8 dimensional hypersurface, it's not really a point, between two adiabatic states. And the remaining 2 degrees of freedom linearly lift the degeneracy in first order. And because it's linear, it has the topography of a double cone, and that's why it's called a conical intersection. Of course, it's a locus of points, and the geometry, if you like, varies along this seam. And I would like to make an analogy that this should remind some of you of the idea of a transition state dividing surface. We know that a transition state is just a mathematical point, and the measure of which is almost zero. So no trajectories really pass through the transition state, but we are quite happy with the idea that along the transition state dividing surface, there's a variation in the geometry. You can think of them as excited vibrational states of the transition state. And I would say, by analogy, we can consider a seam of conical intersections in exactly the same way. So I'm going to argue that a conical intersection is just a transition state in the excited state rather than the ground state, and therefore we should try and learn something from the 30, 40, 50 years of work that has gone into understanding transition state dynamics. Can we learn something? Can we translate some of these ideas that we've learned by many of you in the audience about transition state, the relationship between dynamics and topography, the location, the skew, the tilt, the asymmetry relative to potential gradients? Can we understand this is excited state? Can we understand then diabatic versus non-adiabatic passage? And this should depend on direction and rapidity. This is non-adiabatic dynamics, so the time scales of the approach matter. So I'm going to borrow some notions that came from David Yarkoni, who spent quite some time thinking about this, these coordinates, these two dimensions that lift the degeneracy, and he defined two branching space directions, which he called G and H. Some people who have listened to David's talks call this good and horrible, but he called them as G, the gradient difference vector, which is the direction in coordinate space that leads to the fastest approach to the apex of the cone, if you like. And H is the non-adiabatic coupling vector. It's a direction in coordinate space that maximizes the vibronic coupling. And one of the most important things I want to say is that this is a coupling that depends on a derivative. It's not a potential coupling. In other words, it matters whether you go quickly or slowly. And this is the essential difference. This is a derivative coupling. It's non-local, and it depends on the rates of change. So here's a calculation by my colleague at the NRC, Michael Skurman, who, for this molecule ethylene, has a conical intersection in excited state. And these are these vectors G and H. So G, the gradient difference vector, is the motion that quickly brings these two intersecting states together. And with ethylene, it's torsion largely. It's torsion and pyramidalization. And the non-adiabatic coupling vector, the one that maximizes the coupling, largely is a CH stretch. So it just turns out for this molecule and this conical intersection, these are the two coordinates that sort of form this double cone. And you might expect that trajectories that pass near these geometries will be the ones that are very strongly involved in these conical intersection dynamics. Well, a fair question to ask is a conical intersection really like a transition state? A ground state transition state is a barrier. The trajectories have to climb up to this barrier, and therefore they're slowing down, and therefore they're constrained by energy to pass somewhere quite near this transition state geometry. In excited states, I'm absorbing light, and I can be quite a bit higher than this conical intersection geometry. I can be 1 or 2 electron volts higher. Is this reasonable? Do I require the trajectories to even come close to this geometry? Maybe this is a ridiculous assumption. So I'm going to go back to ethylene again. I'm going to say, let's look at this pi to pi star transition. This is the canonical pi to pi star transition. That's breaking the double bonds. So I take the electrons that were forming the double bond and put them back on the carbons, and they go from sp2 to sp3. The electrons want to avoid each other, so they twist, and because it's sp3, they pyramidalize. And those are the motions. And this motion leads to a degeneracy with the ground state and a very rapid radius of transition and ground state photochemistry. Well, this is from a paper of Todd Martinez, a review article, which is sort of going through how we understood this cis-trans isomerization across the double bond. And to make a long story short, I think everyone accepts now that the conical intersection picture is really the appropriate picture for these types of dynamics. So Todd developed a method called ab initio multiple spawning. I believe it started here in Israel in Raphael Levine's group. And it's a quantum-based method where the basis functions are the classical trajectories. It's an adaptive wave packet method. And the important thing for me as an experimentalist is the on-the-fly calculation of dynamics, the spawning of basis sets. You've heard about this probably many times. But for me, as an experimentalist, the important thing is that this method allows for on-the-fly calculations of observables. I, as an experimentalist, cannot measure wave packets. I cannot measure wave functions. I can only measure observables. So the important thing is that the calculation of time-dependent observables directly from a zero adjustable parameter calculation allows us to directly compare experiment with theory. And this, for me, has been a huge advance in our research. Leticia Gonzalez will also give a lecture, I think, where she will discuss many of these things. So here's a calculation that Todd did a while ago on ethylene. And what he's done here is he's binned the geometry with this stick figure where the non-adiabatic transition took place. And you can see there's a whole range of energies above the minimum energy, 2, 3 electron volts above the minimum energy, and these are the geometries. So interestingly, there is a shape that appears. It's not random. In fact, there does seem to be some shape at which these non-adiabatic transitions occurred, and it looks kind of like the minimum energy conical dissection. So I'd say this is really a good indication that we have some justification in thinking of the conical intersection as a transition state, that the trajectories which have to make this curve crossing, this non-adiabatic coupling to the ground state, do have to pass through geometries that look sort of like that. So I will say this is good enough for me to argue that a conical intersection really plays the role of a transition state in excited state reaction dynamics. So I'm an experimentalist. What about experiments? What can we say from experiments? Well, here's the UV absorption spectrum of ethylene. You can look at resonance Raman, you can look at absorption. You see a progression in the CC stretch and in some twists in parameterization, which is what you expect the molecule to do. But there's no indication in the absorption spectrum of what the molecule does after it absorbs a photon. We know eventually an H atom and an H2 molecule are going to come off, but there's no indication of this in the absorption spectrum. So in other words, what happens next beyond this Frank-Condon region? Well, it so happened that when I was a postdoc in Y.T. Lee's group in Berkeley, we studied this molecule and measured as best as we could the rotational, vibrational, translational energy distributions and the correlations between these, all the vector correlations, between the H2 and H atom elimination from this molecule. And it was a lot of work, I can tell you. And we saw a bimodal product state distribution. We said a lot about it. But this is sort of the last thing the molecule did before it dies. So in a way, I like to say is there's no indication of what happened before the transition state and the ground state. So if I may say it in the following way, that in the lifetime of an excited molecule, its birth is the absorption of a photon, and the last thing it does before it dies is it emits a product. But there's a whole lifetime in between birth and death. And we want to understand what is the molecule doing between the absorption of the photon and the emission of the product. And we couldn't see from these types of data. So this led me, at least, and many other people, to think about methods that are sensitive to the coupled electronic and vibrational changes that occur in these excited state processes. And the technique that we chose is time-resolved photoelectron spectroscopy. Why this? Well, it's because photoelectron spectroscopy is sensitive to exactly the 2 degrees of freedom that you care about, which is the electronic and the vibrational, and the coupling between them. And this cartoon is meant to illustrate the idea that if I absorb a photon to some electronic state alpha, and I consider ionization in a Koopman sense, which means a single photon, single electron process, then if I remove an electron from here, I end up with an ion core, which I'll call alpha plus, just alpha with 1 electron missing. Photoelectron spectroscopy is based on measuring the energy and the angular distribution of this emitted electron. So there's the energy epsilon 1. I've drawn it so that alpha plus happens to be the ground state of the ion. If there is some non-adiabatic process which couples to another electronic state beta, and I make the same argument, this will correlate to some ion core beta plus. It has to be an excited state of the ion since there's no states below the ground state. So conservation of energy says that the electron must have much less energy. This transformation of the photoelectron spectrum is a direct measure of the changing electronic character. At the same time, it's a vibration resolved technique, so any vibrational motions in either the alpha or beta state can also be measured. So this allows us to simultaneously measure both electronic and vibrational dynamics in molecules. That's the reason to do it. I'll just illustrate this with this molecule. A linear polyene has 4 double bonds. Very well known in linear polyenes, dating back to the work of Brian Kohler. So you absorb a photon in the UV, there's a lower lying state, which is dark, and a very fast non-adiabatic process called internal conversion. which essentially is the transformation of electronic into vibrational energy, which is the impetus, the driving force for the ensuing large amplitude motion that we call chemistry. Isomerization would be an outcome, for example. So I'm going to show you the Koopman's correlations in this molecule. It has 4 double bonds, so there's 8 pi electrons. There they are. The pi to pi star transition is like cite this one up. There it is. And the Koopman's allowed ionization would be to take away the top electron. So there it is. All the electrons are in their ground state, so this must be the ground state of the ion. Upon non-adiabatic coupling, we know that it forms this lower lying dark state, and it's dark because it's formed by the mixing of these 3 states, 2 of which contain doubly excited character. If I apply the same argumentation that I remove the top electron from here, I end up in that configuration, which you can see has an electron excited. It's not the ground state. It's the first excited state of the ion. And the same argument here, if I remove this electron, I end up there, which is the other component of the first excited state of the ion. And this one, in principle, would go to the ground state. The point I want to make is that there's a change in the ionization correlation as a function of time due to these non-adiabatic processes, simply due to the changing electronic structure of the molecule. And this is the basis of the technique. And here's our demonstration. This is almost 20 years ago now, where we showed in this molecule that we can see at time 0, we have this Koopman's correlation to the ground state of the ion. The electron comes out fast, epsilon 1. There it is. And as we delay in time, we see that there's a transition to ionizing to the excited state of the ion, which is a much slower electron. And we see a lot more vibrational structure because energy is conserved. I've converted electronic to vibrational energy. And this is now, if you like, a hot molecule. So this is a direct observation which allows us to monitor both electronic and vibrational dynamics in molecules. And since this first demonstration, we've done many, many different types of experiments. But I want to concentrate on my question, which is, can we understand vibrational motions at conical intersections? Can we find any simple rules? Can we apply what we learned from transition state dynamics to excited state dynamics? So in doing so, I'm going to have to take a phenomenological approach. I'm going to have to look at some examples. So we're going to look at this Norrish type 1 photoreaction of aldehydes and ketones. And a classic is acrolein or propanol, where there's 2 chromophores. There's a CC bond, which is sort of like ethylene, would be a pi-to-pi star excitation. And these famously undergo internal conversion and singlet photochemistry. However, there's also a carbonyl group, which is very known for fast intersystem crossing and triplet state photochemistry. So we wanted to understand what is the competition between these processes in these molecules. And our tool for studying this is to use something that we learned from the development of structure-function relationships in organic chemistry, is you vary the structure in a systematic way, and you see what is the effect on dynamics. So our tool for this is to add a methyl group, which is a fairly innocuous electronic effect, but it adds inertia to certain degrees of freedom relative to others. So we're going to move this methyl group to different places in this molecule, and they're called crotonaldehyde, methacrylene, and methylvinyl ketone. And we're going to do a series of experiments and ask, what is the effect of moving this methyl group to different locations in this molecule? So let me just summarize the overall dynamics. This is a pi-to-pi star excitation. There's a very fast internal conversion to this S1 state, which is due to the oxygen. It's the N-pi star state. And from here, there's a competition between internal conversion to the ground state and intersystem crossing to the triplet state. And this is the origin of the alpha cleavage, which is the Norrish type 1 reaction. So these are the products that are typically seen. So usually the intersystem crossing dominates, and this is very well known in the photochemistry of aldehydes and ketones. So we're interested in the competition between these 2 processes. So we did all these experiments on these molecules, and I'm not going to belabor you with all the details, but I just want to point out one thing that surprised us, which is that this molecule, when we put the methyl group only on the ethylenic end here, in the sequential kinetics, this decay rate, the total decay rate of this S1 state, is much, much faster than when we put the methyl anywhere else. In fact, it's almost 3 times faster than when I have no methyl or when I put the methyl in another location. So this was a puzzle. Why does this decay, which goes to both triplet and the ground state singlet, why is it so much faster only in that location? So first of all, is this even correct? The data suggests that internal conversion should dominate now. Why? Because we believe that with the timescales we're measuring, which are around a picosecond or less, that intersystem crossing is already at its speed limit. It cannot be much faster than that. So if the total decay rate of this state is increasing, it must be because internal conversion is speeding up. So if that's true, then I can make a prediction. My prediction would be that if internal conversion is going faster, then the triplet yield should go down, and the singlet yield should go up relatively. These are all known to undergo alpha cleavage, making HCO. So we would predict that very little HCO product would be formed when I put the methyl on the ethylenic end. So, well, that's something that we can measure. So this is looking at the absolute HCO product yield by laser-induced fluorescence. And here it is for acrolein when there's no methyl groups. And here it is when I put the methyl group on that end. So as far as we can tell, it's 0, but I can put a number. It's less than 0.35%. So I have to tell you that I asked some very well-known photochemists like Nick Turrow, Joseph Michel, Tito Scaino, to make a prediction what they would expect when I added the methyl group on that end. And they all predicted exactly the opposite, because a typical organic photochemistry argument is say, well, when I put the methyl on that end, the products are now methyl vinyl plus HCO. Methyl vinyl is more stable than vinyl, so by the Hammond postulate, the transition state comes down, and you should enhance the triplet yield. What this shows is by putting the methyl on this end, the triplet state yield vanishes. And nobody I've met so far was able to predict that. So that's interesting. What happened? How do we explain this? Why is it so much faster? Well, it's not changes in the absorption spectra. This methyl group is a very innocuous substituent. We've measured all these absorption spectra. They're all quite similar. There are slight shifts, of course, but they're very similar. It's not density of states. In fact, because I'm putting a methyl group in different locations, the total density of states remains roughly the same. So I can't argue it's density of states. And it's not energy gaps with respect to triplets. First of all, the methyl has a very small effect on the single triplet energy gap. And secondarily, we're 2eV above the energy gap. So you would not expect to see big effects. So we don't really have a clear explanation yet. Could it be that these conical intersections are very different? Well, Todd Martinez had calculated these and calculated these G and H vectors, which are parameterized by all these things. To make a long story short, it's not the conical intersections being different. They're, in fact, all very similar to each other. So here's what we think is going on. The biggest effect I have when I put the methyl group here to make this molecule than anywhere else is I slow down the torsional frequency. In any other location, this end can still twist very quickly. So when I was a boy growing up in Canada, I used to skip stones in the water. And from a structure function point of view, you'd say, well, the stone is always the same, the water is all the same. Why should it matter whether I throw it quickly or slowly? But if you've done this, you know it does matter. Okay? So dynamics matters. In this case, what's happening is the branching ratio between skipping across in a diabatic way, this conical section, or falling down the hole in an adiabatic way, depends on this torsional velocity. So when I have hydrogen atoms, it goes very quickly through and ends up skipping over this conical section and then bleeding over to the triplets. But when I add a methyl, I slow down that torsion so that it actually falls down the hole in an adiabatic process and ends in the ground state, turning off the triplet channel. And this is what we think is going on. So this, to me, suggests that dynamics actually matters. And we need to think about dynamics because we would have really made the wrong predictions even on the product yields. Okay, so I'd like to digress with something which will be a source of amusement to some of you. I'd like to remind you about something that we call the chromophore. The chromophore is a broadly applied and useful concept. The idea that somehow one part of the molecule is absorbing the light. We know this is not correct. We know that eigenstates are delocalized. The whole molecule absorbs the light. But nevertheless, the idea that part of the molecule absorbs the light is a very useful concept. So I'm going to take this idea and I'm going to say, well, we have seen in many cases of excited state dynamics that the dynamics seem to be localized in a particular part of the molecule, maybe a carbon-carbon double bond or something else. But there seems to be a critical geometry, and they seem to be localized. So with your permission, I'm going to call this the dynamaphore, the part of the molecule where the dynamics become localized. Okay, so I'm going to take another example, again in my phenomenological approach. I'm going to look at these two molecules, cyclohexene and 1,4-cyclohexadiene. The difference between these molecules is that here I have a single carbon-carbon double bond. So there's my pi to pi star excitation. You can think of this as a substituted ethylene once again. But here this is different. Here I have two ethylenes which are coupled to each other with a through bond coupling. And the coupling is strong. The splitting due to interaction is about 1 electron volt. So that's a very strong electronic interaction between these two ethylene units. So we're going to compare these two, and we want to understand what is the effect of creating a localization through absorption of light where there's only one, where because my laser bandwidth is not like Ferentz's, it's much narrower than the 1eV splitting. So therefore, I can only prepare a state which is either the in-phase or the out-of-phase combination of both. So in other words, a delocalization which is necessarily delocalized over the molecular frame. This was the experiment. Here's the result. Again, without going through the details, we studied these molecules, a lot of data, a lot of fitting. Here's the answer. These two molecules display very, very similar dynamics despite this very strong homoconjugation. The diene, interestingly, behaves dynamically as if it had only one carbon-carbon double bond. So this is now my question. How do we go from a delocalized excitation to a localized dynamics on such a fast time scale? Michael Skurman at the NRC had done some calculations, and theory again supports this idea that in fact the conical sections are very much the same, even though there's two double bonds. The dynamics are slightly different in time scale, but the types of geometries, the intersections you pass through are very similar. These ethylenic type of conical intersections. So the interesting thing is that although we have measured this and experimental theory agree, we don't really have a good idea yet why the excitation gets so localized. So here's, I think, a hand waving, but I think probably a correct explanation, is that this is a through bond coupling which is mediated by these central carbons. There is a large amplitude motion in the excited state, so one of the important coordinates is this angular deformation, which is sort of the window by which these two ethylenes are talking to each other. If upon large amplitude motion, I deform that frame such that the ethylenes are no longer talking to each other, then this degeneracy will vanish, and essentially the two ethylenes will become degenerate. If that happens, then in fact, any other vibration can now mix the in-phase and out-of-phase combinations of these two, and I get localization. Once that happens, this molecule thinks it's ethylene and will undergo the dynamics of ethylene. We've seen this in many, many unsaturated hydrocarbons. Once it thinks it's ethylene, it behaves like ethylene, it twists and parameterizes in 20 femtoseconds in the ground state. So we think that this is exactly what's happening here, that the dynamical localization. One interesting question to me is this a more general paradigm? Can this idea of the localization of dynamics due to a large amplitude motion apply more generally? And I think it's a very interesting question. I'd be happy to discuss it with some of you. Okay, so will there be Polanyi rules for dynamics of conical intersections? Will there be early and late barriers? Can we build models? Well, the truth is, I don't know. So again, I'd like to take a phenomenological approach and look for evidence of some trends. So sticking with my ethylene theme, we're going to actually take ethylene and we're going to add methyl groups in different locations, and we're going to excite now to a pi 3s state. We want to see this dynamics from pi 3s to pi star, and how does it depend on these things, and can we look for things that remind us of Polanyi rules? So this is a excitation here. There's a curve crossing, a Rydberg valence curve crossing, and then finally back to the ground state. One thing that I have to point out is that in this case, the methyl group does have an electronic effect, because what happens is that the methyl group actually stabilizes the Rydberg state relative to the valence state. And this is known. It's known from the spectroscopy. It's known from the electronic structure calculations. So here's the torsional angle. And as we methylate, what happens is we stabilize the Rydberg state relative to the valence. But if you look at where the curve crossing occurs, what you see is that along the torsional coordinate, the point, the displacement where they cross changes. So we, again, did many, many measurements, many experiments. I'm not going to tell you in detail, but the summary is this, that as we increase the methylation by adding 2, 3, and 4 methyl groups to ethylene, we see that the lifetime of this 3s Rydberg state is continuously increasing. So here are the calculations of these G and H vectors, which I don't expect you to really be able to see. But to make a long story short, upon methylation, the torsional angle of the conical section is increasing, and the parameterization increases. It starts to look more like a pi-pi star, more product-like. So this leads me to the following picture. Here is the twist degree of freedom. There's the initial excitation. So if you like, that's the reactant, and that's the product. And here is the location of the conical section when I had 1, 2, 3, and 4 methyl groups. And what you can see is that as I add more methyl groups, the location of the barrier is further along the torsional coordinate, and the barrier increases. So in the language of John Polanyi, I would say this is an early barrier, which is more Rydberg-like, and this is a late barrier, which is more valence-like. So maybe there's some merit in thinking along these lines. I'd like to conclude with some future directions. We were asked by Raphael to talk about where we think future directions may lie. And so I'd like to talk about something that we started originally by theory. I was inspired to think about this because I served for 3 years on the proposal review panel of the LCLS at Stanford, and I had to read many of these proposals, and it started me thinking about what would be interesting measurements to make in time-resolved X-ray spectroscopy. The reasons for doing this are not only because of the advances in these free electron lasers, but also in the tabletop sources. And Ferenc gave a very nice explanation about the new opportunities that tabletop lasers now provide in the soft X-ray regime. Conceptually, this is a spectroscopy based on core electrons. Core electrons allow us to view electronic dynamics from the point of view of specific atoms because different atoms have different edges. We can essentially view electronic dynamics from the point of view of different atoms, and I think that's the merit of the technique. So in X-ray spectroscopies, as you know very well, I'll just remind you that we have 2 regimes. One is below the edge. You are taking a core electron and populating it into either an unfilled or a half-filled orbital. Post-edge, you're going directly to the continuum. So here we have bound-to-bound selection rules. These are similar to electronic spectroscopy. So symmetry rules apply, and this is a probe of electronic structure and non-adiabatic coupling. It's very similar to time-resolved electronic spectroscopy or photoelectron spectroscopy. Here, this is the direct ionization. This is the regime of NEXAFs or XANES or XAFs, and it's a well-known probe of structural dynamics. So we're going to go back again to ethylene because this is going to be our model. This is a calculation by Todd and Michael showing, again, ethylene dynamics, the pi-to-pi star excitation. There's a curve crossing with this 3S Rydberg state I was talking about. And the conical section is, as always, this parameterized twisted geometry. Okay, so this is the result of a on-the-fly calculation. I told you that the merit of these on-the-fly calculations is it allows you to calculate an observable on the fly. Up till now, we've been calculating photoelectron spectra. Here, we're now calculating X-ray absorption spectra using the same trajectory dynamics. Okay, so this looks a little bit like scrambled eggs, or maybe in Israel it looks like shakshuka. How do you interpret these things? Well, there's a pre-edge and a post-edge. And what you can see is there's something there, but really let's admit that all the details of the dynamics seem to be in this pre-edge region. So I will just concentrate on this part. There it is blown up. This is would be the transient absorption spectrum in the soft X-ray regime from 0 to 150 femtoseconds. And there's a lot going on. However, this is a calculation, and the big advantage is we have the trajectories. We can look and see what is going on. So we can assign these things. So here, this feature is the initially formed states. So this is the X-ray absorption of the pi star excitation. Later on, we can see that there's this 3S Rydberg state, which is formed by this curve crossing. And then finally, we see all this shakshuka here due to the hot ground state. And we can assign all those as well. However, the interesting dynamic seems to be happening in the first, let's say, 50 femtoseconds. So let's look a little bit closely there. So I blow this up here, and there's lots of interesting things going on. It looks hard to assign, but you'll be surprised to learn that we can actually assign everything there because we can look carefully at this trajectory data and make correlations between what the molecule is doing and what the X-ray absorption spectrum is telling us. So what we see is initially this fast torsional motion, which leads us, there's twist angle, and the wave packet splits And you can see the slope of this is due to this large amplitude torsional motion. And we see it crossing from the pi to pi star to the 3s Rydberg state, where here you can see the slope is not as great, it's slowing down. We can see it coming back again, where it crosses back again. And we can even see it a third time through. So we can see this wave packet passing 2 or 3 times through this conical intersection. However, there's one thing that we didn't assign. There's a feature here in the absorption spectrum that we did not assign for quite some time. We didn't know what it was. We could assign almost everything else. We didn't know what this was, I am embarrassed to say. So at some point we said, well, we have to take the trajectory data seriously. What is the dynamics actually doing right here? So the first thing to note is that this is a transient. It's a transient feature that appears between this 3s Rydberg state, and then it's gone again. So what is this transient? Well, the other thing we notice is actually that there's a pair of them which are correlated. And so there's a splitting of about 4.5 electron volts. So some of you may already guess where I'm headed to with this. This splitting is actually due to the fact that at the conical intersection, you have a transient polarization, what's called sudden polarization. You have a separation of charge, and the 2 carbon atoms become inequivalent. So there you have it. So our explanation for this sudden, this splitting of the peaks seen only around the conical intersection region is due to this sudden polarization phenomenon, which is well known in ethylene. And this splitting may seem large to you, but if you actually look in a textbook, what is the splitting of the 2 inequivalent carbons in a molecule like fluoroethylene, it's about 3 electron volts. And if you do some Mulliken charge analysis or something maybe a little better than that, you'll see that it really is very sensitive to this separation of charge. So in that sense, I would say that X-rays, ultrafast X-ray spectroscopy really could be a spectroscopy of conical intersections, which would be very exciting. This paper is just been accepted. However, I'd like to point out that Shal Mukamel will be talking about even more sophisticated coherent X-ray probing of conical sections, and so for that you'll have to wait for his talk. So my conclusions. Conical sections I think we can think of as transition states of the excited state. We need observables which are sensitive to both electronic and vibrational dynamics. I would argue that we should calculate the time dependence of observables so that we can directly compare with the experiment. And I would say, as with transition state theory, there's a need for simple models of dynamics of conical intersections. Perhaps the planning rules will apply, perhaps they won't, I don't know. We're going to see how far we can go. And my main take-home message is that I think we need to bring dynamics into a more equal footing into our ideas about structure-function relationships. So I'd like to acknowledge a particular acknowledgement. This is my good friend, the late Moshe Shapiro, who I interacted with for nearly 30 years, and I learned many things over many discussions with Moshe. That's the National Research Council in Ottawa, where I did much of this work, and these are my colleagues. Especially like to acknowledge almost 15 years of collaboration with Tom Martinez in his group, which really have taught me a lot about excited state dynamics. With that, I'd like to thank you for the chance to talk today.
You're certainly aware that many of the photochemical processes take place over a large span of time scales. One concern is, and I think it's almost known for a fact, that formation of products can take place a long, long time after the crossing of the potentials. That might change the situation. And actually, I would like to add in this respect, I think, the field owes an enormous depth to these great and very insightful Polanyi rules. But the truth is that if you go beyond A, B, C, potential surfaces and experiment have taught us, the more complicated and polyatomic the system begins, we see also deviations. So maybe these two things are related.
I'd like to, well, I have a long answer to this, but I'll give the short answer. I think the short answer is that these are gradient-directed dynamics, particularly for the case of carbon-carbon double bonds, where you have strong slopes and you're passing through these regions of non-adiabatic coupling very quickly. So from that point of view, it's actually not possible for all the degrees of freedom to really participate actively in the dynamics. There's only a few. The decision-making, the branching, often can occur quickly. Of course, the photochemistry can occur long afterwards. But as I showed in these examples of these unsaturated aldehydes and ketones, that this is why we made the measurement of the product yields. That the decision-making is done in the femtosecond timescale, but once you're in the triplet manifold or the ground state singlet, the ensuing chemistry can take as long as it likes because the decision of the branching has already been made. And so the question is, can we understand something about this branching between one type of pathway and another, and is this dependent on details of how quickly and from what direction we pass through these conical sections? And I think we have some evidence that it matters.
We have time for one last question.
After excitation, the energy can sort of remain localized for a while, or it can get diffused through the many degrees of freedom
of course it
molecule. What is the time scale for that remaining localized, and do you have data which reflects that time scale?
That's a good question. We have very little data, except I can show you that, so of course we see not only these curve crossings, which we relate to our photoelectron spectra, but we can see that there is an evolution of the photoelectron spectrum after the crossing. So these are vibrational dynamics, which we know must be there following the initial curve crossing. So a simple picture would be in this linear polyene molecule that I showed you earlier, if I can get back to it. So you see that you can actually, this is a internal conversion, classic case of these linear polyenes, where this is now the dark AG state, and you can see that this is the photoelectron spectrum of this dark AG state, and there is vibrational dynamics there. This molecule happens to have 66 internal degrees of freedom, so it's hard to characterize it, but we certainly see evidence that there's ensuing vibrational dynamics following these curve crossings. It would be very nice to get more information about this, but this, of course, as you know very well, is a difficult problem. Our goal was really to try and understand what governs the initial branching between these two. The ensuing vibrational dynamics, and including the dissociation which occurs, is a well-known and complex problem. But the initial branching, I think, is something that we can maybe influence. It was a surprise to many photochemists that putting a methyl group in different locations could completely change singlet-triplet branching ratios, for example.
So apart from the branching, are you showing there that at least within 400 femtoseconds, the energy is sort of remaining localized, but it's moving around?
I think it's really highly dependent on the nature of the molecule. I think that we know that non-adiabatic couplings are mode dependent, it's coordinate dependent, and there are certain modes which will be populated, but you end up in a highly vibrationally excited vibrational state of a lower-lying electronic state. So, of course, there'll be lots of intramolecular vibrational energy redistribution which will set in and mix all those degrees of freedom pretty quickly. So we expect that IVR, if you like, will follow these crossings pretty quickly, and it then depends on the details of where the crossing is relative to the origin, the density of states, all these types of things.
So there is no universality?
There's no universality, but I guess I'm arguing, and this is why I like this illustration of these unsaturated aldehydes and ketones, is that I think we still need to bring a dynamic picture into our notions about structure-function relations. So if you learned only one thing from what I said today, I'm hoping that you'll agree that we need to bring dynamics in a more equal footing.
Okay, with that on, thank you again.